Hello, everyone. We are working through an introduction to statistical methods and data analysis by Ott and Longnecker, chapter 11, part 3. So in this section, we're going to be talking about the total variability that we can see in our response variable. So overall, if we have some linear regression model and we have our data points that fall around this line, we know that y bar, we'll use a dashed line for y bar, is going to lie on the line, right? And we could think about the distance from each of these data points to the y bar, right? Because in general, all of these can be calculated yi minus y bar for each of the observations. And we know that if we just think about all the observations minus the mean, that they would all cancel each other out. But if we think about the distance squared, now everything's positive and there's no way for them to cancel out. So if we think about the summation of the yi minus y bar squared from 1 to n, that gives us our total variability, or our sum of squares total. So in partitioning the total variability, we could add and subtract out a y hat I. So right here, we've added and subtracted the same exact y hat I. So we haven't really changed the equation. And then we can change the grouping, right? Which doesn't affect anything, but just saying, let's group these two things together. After that grouping, we can FOIL to be able to get these results. So we'll have 3 pieces, right? One is our sum of squared errors, right? This first piece, our yi's minus our y hat i's, right? Those have i's under them. And then we have this middle piece, right? Which I'll add some lecture notes that does the full proof, but essentially we're going to note that this is going to be equal to 0, that whole piece, right? And then our last piece is our y hat i's minus our y bar squared, okay? That piece is going to be called our sum of squares due to regression. Okay, so essentially we can partition this total variability into 2 pieces, right? So we have our sum of squares total equals our sum of squared error, which is the unexplained variability, plus the sum of squares due to regression, which is the variability that can be explained by the model. Once you do this, you could then calculate your coefficient of determination, right? So we have SST, right, is equal to SSE plus SSR, right? So if we divide all of this, each of those pieces by SST, what do we get? We get 1 equals SSE divided by SST plus SSR divided by SST, right? And this piece right here is a proportion, right? That is the proportion of variability in y that can be explained by the linear regression model, okay? So we can solve for SSR over SST, right? We get 1 minus SSE over SST is equal to SSR over SST, right? And using some algebra, we can find that r squared is equal to sxy squared over the sum of the x deviations and the sum of the y deviations. Now, this isn't something that you need to memorize because you have formula sheets, and in the workplace, you'll be able to look up these formulas. The really more important part is, what does the coefficient of determination actually do? It's telling you whether or not your line is a good predictor of reality. It tells you how much predictive power the variables in your model have. So if your r squared value is very close to 100% or close to 1, then you have excellent predictive power. If it's between 50 and 80%, good predictive power. 25 to 50%, fair. 0 to 25%, weak. One of my old students told me an acronym is every good friend wins, right? So excellent, good, fair, weak. But overall, you just have to think that it's the best when it's close to 100%, and it's the worst when you're closest to 0, right? So the larger the ratio is, the more variability we can attribute to the variables in the model. The smaller it is, the less we can attribute the variability to what's in our model. So I hope you learned something about the coefficient of determination, and I'll see you next time.